Hello students, I am Kalyani Vable and welcome to the Department of Mathematics of KTHM College, Nasik. Here we are going to study Mathematics paper first, groups and coding theory of S.Y.B.Sc Computer Science class.
In previous video, we saw integers, division algorithm, GCD and their examples. Now today, we are going to study well ordering principle, proof of GCD is a linear combination and Euclid's lemma. Okay. Now today, we start with the well ordering principle. Well ordering principle. Statement: every non-empty set of positive integers contains a smallest member. So see here, if we consider any non-empty set of positive integers, then it must contains a smallest member. For example, set of natural numbers 1, 2, 3, 4 and so on. So here smallest member is 1. Okay. So this is the example of well ordering principle. Now this is infinite set. Now here next example, we consider the finite set. Suppose A 4, 8, 12, 16 and 20. So set A is finite. So here smallest member is 4. So this is again the example of well ordering principle. Now we consider the next example, set of integers. Minus 1, minus 2 and so on. 0, 1, 2 and so on. So here this set contains the negative numbers, 0 and positive numbers. So here in this example we can't tell about the smallest member. So that's why this is not the example of well ordering principle. Okay. So in short, remember every non-empty set of positive integers contains a smallest member. Get it? Okay. Now next point, GCD is a linear combination. Theorem. GCD is a linear combination. Now statement: for any non-zero integers A and B, there exist integers S and T such that GCD of AB is equals to A into S plus B into T for all S and T belongs to the set of integers. Moreover, GCD of AB is the smallest positive integer is of the form AS plus BT for all S and T belongs to the set of integers. So see statement, for any non-zero integer A and B, there exist integers S and T such that GCD of AB is equals to AS plus BT for all S and T belongs to the set of integers. Moreover, GCD of AB is the smallest positive integer, is of the form AS plus BT, where S and T belongs to the set of integers. Okay, now we see the proof of this theorem. Proof. So here we consider the set. So consider the set S equals to, the elements is of the form AM plus BN, as M and N belongs to the set of integers subject to the condition that AM plus Bn strictly greater than 0. Okay, so we consider this set S, elements of the form AM plus Bn, as Mn belongs to the set of integers and condition AM plus Bn strictly greater than 0, that is positive. Okay, observe that AM plus Bn is an integer. AM plus Bn is an integer, and here AM plus Bn greater than 0. Condition is AM plus Bn greater than 0. So that means this set S is a subset of set of natural number. Okay, so that means we get S is subset of natural numbers. Now note that A and B belongs to set S. A and B belongs to set S, and if we take M equals to 1 and N equals to 0 or vice versa, then we get S is a non-empty set. Then we get S is non-empty set. Okay. Now we all know the well ordering principle. Every non-empty set of positive integers contains a smallest member. Now see here, we show that S is non-empty. So here, by using well ordering principle, S contains a smallest positive integer D. Okay, say D equals to AS plus BT for all S and T belongs to the set of integers. Give it to the number first. Now here, by using well ordering principle, we get a smallest positive integer D is of the form AS plus BT. Now claim D is a GCD of integer A and B. D is a GCD of integer A and B. That is, first we want to prove that D is a common divisor of A and B. D is common divisor of A and B. And then we show that D is greatest among all common divisors of A and B. Okay, so first we want to show that D is common divisor of AB, and after that it is greatest among all positive divisors of A and B. So here again we claim that D divides A. Claim D divides A. Okay, so we prove this by using contradiction method. So by contradiction, we assume that D does not divide A. So by contradiction, we assume that D does not divide A. So by using division algorithm, A is equals to D times Q plus R, where 0 less than or equals to R, strictly less than D. So this is division algorithm. Now from equation number first, D is equals to AS plus BT for all S and T belongs to the set of integers. Substitute this equation here. So we get A is equals to AS plus BT into Q plus R. Now simplify this equation. So we get A is equals to AS into Q plus BT into Q plus R. Now here we want to find out the value of R. So R is equals to A minus ASQ minus BTQ. Okay, now again simplify this equation. So we get here we get R equals to, take out A common, so we get 1 minus SQ plus B into minus TQ, where 0 less than or equals to R less than D. So here by division algorithm we get R is smallest than D. That is, here we get R is smallest positive integer, but which is contradiction to the fact that D is the smallest positive integer of S. Okay, so which contradicts the fact that D is smallest positive integer. Okay, so therefore our assumption D does not divide A is wrong. Hence, D divides A. Okay. Now, in similar manner, we get D divides B. So, in similar way, we also show that D divides B. Now, observe that D divides A, D divides B. So, here D is common divisor of integer A as well as B. So, that means here we prove that D is common divisor of A and B. Now D is common divisor of A and B, but here we want to prove that D is greatest common divisor of integer A and B. To prove this result, we want to assume that another common divisor which belongs to the set S of integer A and B. That is, we assume that, or we take another common divisor of A and B, say D dash. Say D dash belongs to set S. Say D dash is equals to AM plus BN for all M and N belongs to the set of integers. Okay. Now here D dash is equals to AM plus BN. That means this implies that D dash divides A as well as D dash divides B. So which implies D dash divides A and D dash divides B. Okay. So here that means D dash divides any linear combination of A and B. So therefore D dash divides any linear combination of A and B. That is, D dash divides AS plus BT for all S and T belongs to the set of integers. Okay. So here that means D dash divides D. D dash divides D. So that means we get D is a greatest common divisor of A and B. That is, D is GCD of AB. Okay. So in short, first we assume the set S, the elements is of the form AM plus BN. As M and N belongs to the set of integers, subject to the condition that AM plus BN strictly greater than 0. S is non-empty set. So that's why by using well ordering principle, there exists a smallest positive integer in S. Okay. So say D is equals to AS plus BT. Now here we want to prove that D is GCD of A and B. So for showing this result, first we want to prove that D is a common divisor of AB, and among that common divisor, D is the greatest common divisor of AB. This is the outline of the proof. GCD is a linear combination. So here we get the result. Okay. Now next point, Euclid's lemma. Euclid's lemma statement: if P is a prime that divides AB, then P divides A or P divides B. If P is a prime that divides AB, then P divides A or P divides B. P divides AB, then P divides A or P divides B. So this is the statement of Euclid's lemma. Now we see the proof of this Euclid lemma. Proof. Here we assume that if P is a prime that divides AB but does not divide A. So here we assume that P is a prime that divides AB but does not divide A. Now there exists integer S and T such that 1 is equals to AS plus PT. This implies that B equals to ABS plus PTB. Okay. Now observe this equation, B is equals to ABS plus PTQ. So here P divides the right hand side of this equation. That's why P divides B. Okay. So since P divides right hand side of equation, also P divides B. So here we get the proof. First we assume that P is prime that divides AB but does not divide A. So there exists integer S and T. 1 is equals to AS plus PT. Here then this equation implies B is equals to ABS plus PTB. Now from this equation we get P divides right hand side of this equation. So P divides B also. Okay. Thank you.